Hi everyone, I'm going to talk today about the NumPy API. So this is the style of programming that we use in PyTorch and JAX and TensorFlow. It's really big first-order array operations called from a dynamic host language like Python. My first involvement with NumPy at a deep level was this project called Autograd. So in 2014, we had this idea that we would try to add automatic differentiation to the NumPy API. Just for clarification, there's also, of course, a Torch module called Autograd. I think since our project, it became a kind of generic term, but I just wanted to highlight that possibility of confusion. So with Autograd, the idea was that we would take every function in the NumPy API and we would wrap it up with logic that would firstly record every time it's invoked, and secondly, associate with each NumPy function a function which computes its derivative, or really its vector Jacobian product, or its pullback. And then with that, we would be able to expose a single higher order function called grad, which would let you take the gradient of ordinary Python functions that involve NumPy API calls inside of them. And this worked out really well. It worked out, I think, way better than we expected it to. And at the time, I think we just thought that we were extremely clever. In hindsight, I've got a different perspective, which is that I think we got very lucky to have chosen the NumPy API. The NumPy API turns out to have a bunch of properties which make it perfect for this sort of application. So firstly, it is closed under AD. You can define the derivative of NumPy operations like sine in terms of other NumPy operations like cosine. Importantly, you can do this without resorting to having Python loops in your derivative functions. This turns out not to be a common property. Once you start adding more and more language features, it actually becomes quite hard to preserve closure under AD. For example, XLA, HLO, what the programming language that JAX targets, does not have this property. Secondly, NumPy exposes a lot of within-op parallelism. So individual ops have loops inside them, both maps and reductions and other loops, and you can write CUDA kernels that exploit that parallelism, and that's of course exactly what PyTorch is. It's one way to look at it is as a GPU-backed NumPy. There's a really neat interaction between the sort of within-op parallelism that NumPy exposes and this closure under AD, which is that as an implementer of an AD system, it doesn't matter if your implementation is actually serial, even kind of slow. As long as the forward pass uses NumPy operations and has a lot of within-op parallelism within those ops, then the backward pass will use similar NumPy operations and will have similar parallelism within those ops. And so you'll have a parallel backward pass as well as a parallel forward pass. And there's very little you need to do at the implementation level of AD to have to worry about parallelism. It turns out that as you start making more and more complicated language, it becomes quite hard to preserve parallelism under AD, and actually it's a sort of active research area. But there's a third property, which is actually what I'm going to focus on mostly in this talk, which is that the NumPy API really lends itself to being an embedded language inside a host language like Python. And the reason for that is that it's a first-order API. So it's composed of a bunch of functions, and each function is a first-order array function. You ship it data arrays, and it gives you back data and arrays. And from the programmer's point of view, it's just like any other Python library, right? Once you make a call to a NumPy function, you can query the results, and you can look at the values, and you can print them out, and you can do anything else. You might have thought this would break down once you start doing differentiation, because grad is a higher order function. You give it a function, and it gives you back a function, and who knows what's going to happen. It turns out, though, that grad is actually a very special sort of higher order function because it only augments the original function. So when you differentiate a function in PyTorch or in Autograd, you can still do things inside the body of that function, like you can print out values, you can branch on values, you can log stuff, and the semantics will all be pretty predictable. So it turns out that the grad plus NumPy is a really really sweet spot of a programming model, and we were sort of lucky to stumble on it in Autograd, and PyTorch has really taken it to the next level. So if it's such a great model, why do we even need to have anything else? And of course, the reason is that not everything is a NumPy kernel, right? As soon as you need loops, and those loops don't already exist in a NumPy kernel, then you have a performance problem. So here's a simple example. Let's say we're simulating the dynamics of a particle by evaluating its energy or forces on it at each position, and then changing its momentum and position accordingly. And we're doing this in a loop. So this is a very sort of common thing to do. There is no NumPy kernel for this, of course. There's no PyTorch kernel for this. So you're going to have very bad performance if you write this as is in Python, because you're going to have a host level, host language, host machine loop that's not going to go very fast at all. And it's a real shame, because this is such a obviously parallelizable program, right? It's an embarrassingly parallel map of a function whose like in a loop is just a single for loop. Now, the NumPy model does offer a nice escape hatch, which is that if you do have a performance bottleneck, you can always write your own kernel to address that. But even that actually isn't possible here, because this is a higher order function. So you might be able to write a kernel that computes this for a particular choice of energy. But if you want to write this as a library function, and you want users to be able to call it with their own energy functions, then you're actually out of luck. There's no way to do that, because this fundamentally is a higher order API, and you can't expose a higher order API in a performant way using the NumPy API. So this is a real problem. The same property that makes NumPy so embeddable, the fact that it's first order, also limits its expressiveness. So this brings me to JAX. So JAX, it was sort of the second generation of this project that started with Autograd. And one way to think about it is that as a first approximation, it's just NumPy plus AutoDiff. But then on top of that, it starts to add these higher order functions, and some of them these sort of so-called second order array combinators, like map, reduce, scan. Map being something that does the same thing to each array element, reduce being something that summarizes the elements in an array, and scan being a sort of sequential iteration. So here's an example of just like evaluating the nth Fibonacci number using JAX. So you can imagine that what a Python for loop version of this would be. Instead, with JAX, you have to do some syntactic changes. Instead of having a for loop, you sort of write a function that represents the body of the computation with an explicit carried state, and then you use scan to apply that iteration again and again and again until it computes the nth number. And then what's going to happen when you call this is this body function, unlike an ordinary Python for loop where the body gets executed n times if there are n iterations. JAX will only execute this body once, but it will execute it abstractly with sort of special JAX values that contain information about shapes but not about values, and then it will create an abstract representation of that function abstracted to the shape level that it can then hand off to XLA, and then can compile the entire program to perhaps a single GPU kernel or a TPU program. So JAX really does let you take these higher order functions and compile them. So here's that particle simulator example in JAX. Same sort of story. So there's this syntactic change where you have to express it as a function and then a higher order function acting on that, and we write vmap instead of map. But otherwise, it's pretty natural. So what's the problem here? The problem is that you pay a very steep price in terms of the naturalness of the embedding. So the semantics of this library simulation function are very different from what you'd get if you'd written it in pure Python. And let's look at an example. Let's say as a client of this library, I want to have an energy function which saves some work by only evaluating energies of nearby neighbors to the particular particle of interest. So at each step, I'll examine which neighbors are nearby, I'll ignore all the others, and I'll just evaluate the pairwise energies between me and those neighbors. This is an extremely common thing to do in all sorts of simulation and ray tracing and other things. The problem is that if I try to give this to the simulation function in JAX, it'll throw a pretty inscrutable error, which is that it'll complain that we haven't given it a statically shaped body. And the problem is that this sort of language that JAX embeds, this JAX IR, expects shapes to be concrete shapes in the type system of the JAX IR. So this sort of program gets thrown out. Similarly, if you try to throw print statements in here, bad things will happen. Or if you try to sometimes return nothing because there's an exceptional case, and sometimes return the value, bad things are going to happen. So JAX does manage to expose these higher order combinators in Python, but it does so at the cost of making the embedding much less natural and obvious, right? There's increasingly a conflict between the semantics of the embedded language and the semantics of the host language. And this brings me to what I sometimes describe as the embedded DSL talk bit, right? As you add more and more language features, you might be improving performance and you might be improving expressiveness, but you're always making the quality of the embedding go down and down and down and down. And it's almost heartbreaking to think that we could we could improve JAX, right? We could add support for dynamic shapes and for sum types and all these other things. But every new feature we add, we're going to make it more and more awkward for programmers who are using these features from Python because of the mismatch between the embedded language semantics and the host language semantics. But there is a silver lining here, and that's that as we do add more and more features, it starts to become more and more feasible for the language to be a standalone language, right? At some point, it can stand on its own 2 feet, and we can actually get rid of the host language and have a language that's custom built for exactly these sorts of numerical array-oriented differentiable programs. And that brings me to DEX. So DEX is exactly an effort to do this. So it's the 3rd generation, if you like, of this project that started with Autograd through JAX and now this language DEX. It's a functional, statically typed language, very much in the spirit of OCaml and Haskell and ML. It adds some typing system features that are sort of specialized for arrays. So array shapes are actually encoded in the types, and as well as that, it has all the nice things that the functional languages have given us, like algebraic data types and type classes and all of that. But importantly, it's built around 2 key pillars, which are parallelism and AD. And as I alluded to earlier, the interaction between those 2 is actually turns out to be quite subtle. I don't have time to go through a full demonstration of DEX and what it is and where it's going. But I'll give you just the particle simulator that I showed before. This is how it looks in DEX. Very similar in many ways. One thing I will draw your attention to, though, is that we do get these pretty precise types that we can use to describe these functions. So now finally we see that energy actually is a function, right? Before you had to figure that out from how it was used. Here it's obvious that energy is a function from A to float. A is what? A is the type of the position and similarly the type of the momentum. And you can see that they're all the same A, and that they're constrained to be a vector space because you have to add them and scale them. So the type of this thing and the parametricity of that type are very explicit in the syntax here. Similarly, once we start to simulate many particles, we'll see that the number of particles that we give to simulate many is the same as the number of eventual positions that we get as a result, because again these shapes are encoded in the types. And then we can give it a function that uses dynamic shapes internally, and of course everything's fine. There should be no reason to ever get an error other than a type error when you try to differentiate or parallelize or anything like that. Okay, so that's it for me. The main takeaway is that I'm a big fan of NumPy as an API. It turns out to be a perfect fit for doing the kind of differentiable, parallel, GPU-oriented computing that we do a lot of. But it is super limited, and I really hope we can move beyond it. JAX is moving beyond it in particular ways at the moment, and it's ready today, and you can use it. Some of the embedding problems that the JAX runs up against, I think, is solved in our next generation, which is this language DEX, which is far from being ready, but maybe will be in a year or 2. Thank you so much.